Yeah. Okay, guys, welcome to our quantum error correction workshop. If you need the attendance form, they're still up here. So last call for that. If you need the QR code, that's also up there for the workshop notebook. Feel free to follow along or just watch. And this will also be sent out after the meeting is over for anyone who wants to, like look back on the notebook or reuse it or anything like that. But yeah, if no one else needs the attendance form, I guess we can go ahead and get started. So if I can exit, there we go. So the topic of today's workshop will be primarily quantum error correction, and we'll also show you a sample of our own project work, LogicalQ, which is the quantum error correction library that we work on here at QCA. So let me zoom in a bit. So yeah, if you came to last week's workshop, then some of the basics of quantum computing in general, and that stuff's like generally applicable to different areas of quantum computing. But today we're going to focus specifically on what we do in quantum error correction. So we'll talk more about like why is this important and what are we doing as we go on. But to start out with, as always, we have to import stuff. So for the first half of this, we're going to be using Qiskit. So this is all just like IBM Qiskit library stuff. So nothing that like we personally developed ourselves, but it's good to like show you like what's actually happening behind the scenes with Qiskit. Yeah, you import this stuff, and just like last time, these are really important libraries. You'll always be importing them whenever you use Qiskit. And so we start out by making a quantum circuit, like always, right? So we import stuff, we make these quantum registers and these classical registers, and we put them all into a quantum circuit. So then once we have a quantum circuit, we can start putting operations. For today, I'm being really, really boring, and the only operation that we've put is a single Pauli X gate. If you remember from last time, all that this does is it flips zeros into ones. So if you forgot, whenever you have a quantum circuit in Qiskit, everything starts out in the zero state. So we have a single qubit here, and it starts out in the zero state, and we flip it from 0 to 1. That's all that this quantum circuit is doing. So it's really boring, but it's going to help us, at least for today, to show like what's actually happening with noise and quantum error correction. So one thing that you can do, well, let's run this. That's one thing you can do. And yeah, you can visualize the circuit and you can verify what I told you. It's just a single qubit, single classical bit. We do a Pauli X, and then we do a measurement. So we sort of talked about measurements a little bit last time, but we sort of rushed. So I'll say it just really quickly. Measurements are just how you figure out what state your qubits are in. And you can't just measure your quantum circuit once. You have to do measurements many, many times in order to collect statistics about your state and to do like characterization and just general analysis. You always need to do multiple measurements. If you do know the exact quantum circuit and you have no noise, you can compute a state vector. So this is something that we used a lot last time. It's basically just taking your quantum circuit and it's computing the exact quantum state that will be output. So just like I said, it starts in the 0 state and you end up with a 1 state, right? That's all that's happening. Right now, there's no noise in the state vector computation. It's exact, it's perfect. It's using linear algebra to compute the exact outcome of the circuit. But in reality, when you're working with a quantum device, a quantum computer, there's going to be a lot of noise. And, you try and beat down the noise from a hardware perspective. That's what experimentalists do. But you can't get rid of every single bit of noise in your quantum circuit. So, yeah, question?
By noise, can you just give examples of like what you mean by noise? Is that
Yeah. Yeah, so a noise, an error just represents, or noise error, however you want to call it, is just anything that can happen to your quantum circuit while it's executing that affects it in a way that you didn't want to occur. So you have quantum operations that you do yourself, and then you also have quantum noise and quantum errors. Okay, so you can represent quantum errors as operations too. They're just not operations you did. So there's a couple examples of different types of noise that can occur, and the exact examples depend on what quantum device hardware you're using, what modality you're using. But in general, you have things like magnetic fields, electric fields, temperature, even just vibrations, anything like that. Sound is a vibration, so that also affects quantum computers. But basically, anything that's physical can affect your qubits. So we can model that using something called a noise model. Shocker, right? So a noise model is something that we can construct. Qiskit has their noise model class, and a noise model is just a general thing that just says, this is how noise behaves on a quantum circuit. So we did a state vector simulation, which is exact, but we can do a noisy simulation with the noise model. And so don't worry like what this noise type in particular does, But basically, depolarizing error is a type of error that can occur to your quantum circuit. So every time you try to do a quantum operation, you'll instead get some function of quantum operation. So this is sort of like what we talked about a little bit before, where you mean to do an operation like u, right, where u might equal x or Hadamard or y, z, c naught, whatever. But instead, what you end up with is you end up with some function of u. So like e of u, okay? And that's the operation that you actually implement. A noise model just says, what is e of u? How do you go from these exact u operators to these noisy e of u operators? And so depolarizing error is just one of those. And so it takes a parameter, which is basically the probability of an error, roughly, not exactly, but it roughly corresponds to that. And then it takes how many qubits you're doing the error on. So here we only have 1 qubit, so we have single qubit errors, right? If you have 50 qubits, you have single qubit errors, you have 2 qubit errors, you have 3 qubit errors, and you have all the way up to 50 qubit errors. So you can see why big quantum circuits are really noisy and why you need quantum error correction to scale. But for now, we're just dealing with 1 qubit to keep things simple and easy to visualize. So yeah, you can make a noise model. This is just another import from Qiskit, and then you can add a quantum error to it. So we added this depolarizing error. And something that's special about errors is that they can occur on different types of gates differently. So in this case, I just said that this error only applies to X, Y, and Z gates. If you don't remember, these are the Pauli X, Y, and Z gates that are really important in quantum computing and error correction. So here I'm just saying, okay, I have an error. It's some special type of error. It has probability sort of corresponding to 0.5, and it occurs on X, Y, Z gates. So what the noise model is going to do is it's going to say, okay, every time I see an X, Y, or Z operator, I'm going to replace it with a noisy X, Y, or Z error. If you're curious about the depolarizing error, the way it works in particular is it says, okay, with some probability roughly corresponding to P, I'm going to do the gate you told me. I'll do X, I'll do Y, I'll do Z. But with the remaining probability, I'm going to do the identity. So that means I'm not going to do anything. So you said, okay, apply an X gate, right? Like up here, we said, can you apply an X gate to our qubit? And with some probability P, it's just not going to do that. It's going to do nothing. So instead of flipping from a 0 to a 1, like our exact state vector says, we're instead going to go from 0 to 0, or from 1 to 1. Does that idea generally make sense? An error is just an alteration to what you meant to do. It's something that you didn't want to occur. So yeah, you can make a quantum noise model, and then once you have a noise model, we can apply it to a simulation. So AIR is this library that Qiskit and IBM developed to do quantum circuit simulations. And so you can say, okay, do a simulation, but using this noise model. And then you do like transpilation and stuff, which we're not going to talk too much about. But you can run your quantum circuit with some number of shots. So here I'm doing 10 to the 4 shots. So that means I'm running my circuit 10 to the 4 times. And I'm collecting all of the data from every single outcome. And so I can run that. Hopefully should run. And then I can plot it. So this is also like the histogram thing we saw last time. And what do you know? I told it to flip it from a 0 to a 1, but that only did that about 75% of the time. So this is where it comes, like I told you, like the parameter is like 0.5. That's not exactly the probability of an error. It's closer to P over 2, so 0.25. And that explains roughly what you see. 25% of the time, we didn't do what we wanted to do. We just did nothing. And that is quantum error, quantum noise right there. I wanted to flip from 0 to 1, but I didn't get that. And there's this question of like, how do you stop this, right? Because one thing you could do is you could say, okay, 75% of the time, that's good enough. You know, like if I do 1 million experiments of the same exact quantum circuit and I collect data and 750,000 times I get a 1, I can say, okay, the outcome is probably supposed to be 1, right? Like you can infer that sort of thing, but that's just not scalable, right? Like you can run the quantum circuit 1 million times, sure, but you're never going to get anywhere. And even if you do run it 1 million times, you're going to still have so many errors, right? Here we had 2 outcomes. We only had a 0 or a 1. So if whichever one has more measurements, we say that's our expected outcome. But let's say, yeah, question.
Can you describe on like the block sphere, what's happening?
Yeah, sure, I can do that. Yeah, so let me quickly like finish that. So even if you do 1 million measurements, if you have this many measurements that have errors. Imagine what happens if there are 50 possible outcomes, right? Like maybe you're saying, okay, I want to factor a number using Shor's algorithm, and I want to figure out which number is going to be the correct factorization, like which numbers are the correct factorization. Then you have infinitely many numbers. So every number is going to have some little probability of being the factor, right? Because of noise. It'll be like, oh yeah, 5% the factor is 1, 2% the factor is 2, 3% the factor is 4, and so on and so forth. All of that data is too noisy. You can't actually say with certainty what's the outcome. So because of that, you cannot just run your circuit a trillion times and hope for it to work. You have to be more careful and smarter about how you correct these errors. So yeah, before we talk about error correction itself and some other things, I can show you on the block sphere what that looks like. So on the block sphere, what's basically happening is I want to take a state which looks like this. Okay, so this is like my 0 state. Okay, and I want to flip it to a 1 state. Okay, I'm going to flip it to a 1 state. And so the quantum operation I want to do is going from 0 to 1, just this reflection. Okay, but what's actually occurring is my outcome also ends up being 0. So that's depolarizing error basically just says stay in that place.
Okay, so it's not like it's flipping it to some other state.
No, okay, so you can have more complex types of depolarizing error, but the one that I constructed here is a lot more simple.
Okay.
It's just saying with some probability, it's not going to occur. Yeah, that's all that there is to it. And there are different types of errors, right? So there's an error that you could say, okay, instead of applying X, right, you could say, you could define your E so that E of X is equal to, say, oops, not that. You could say it equals Y. So every time I want to apply an X gate, I actually apply a Y gate. And that's really bad, obviously, right? Like, hopefully, you're not guaranteed that you'll run the wrong gate. Hopefully, it's like 0.9 or like 0.0001Y and then 99% X, right? That means 99% of the time it'll do the right thing. And that's what these parameters tell you. Yeah.
So I'm assuming you keep using the hat notation for.
Yeah.
Like, not functions, operations.
Yes. Yeah. So in some like textbooks and like papers and stuff, you won't see them use the hat. I think it's really smart to use the hat because there are a lot of pieces of notation that look like operators but aren't operators, or there are things that are operators but don't look like operators. And so it's just better to use the hat. One place where this is true, for example, is CX. Okay, you could look at this and think, oh yeah, that's a C gate times an X gate. That's not what it is. It's a single CX gate. And by putting the hat, that was a terrible hat. By putting the hat, I can tell you this is one gate, right? So there's a million reasons why I prefer to use the hat. If you don't, it's not wrong, it's just notation. But yeah, thanks for asking. And yeah, I guess if you didn't come to the workshop last week, these are just vectors that represent the quantum state. So every quantum state is somewhere along this block sphere. This is the sphere of possible states that your quantum system can be in. And these vectors just tell you where on that sphere you are. And so this is just one type of error where you don't do what you wanted to do. Okay. And so you might ask, like, okay, how do we actually like think about this error stuff, right? Like we said, like, oh yeah, there's like some parameter and like things happen and then you like have some probability of it not working. But we need to like formalize this a bit more so that we can have some vocabulary moving forward. And the way we do this is fidelity. Fidelity is the #1 word in quantum computing. It's what everyone is hoping to maximize. You'll hear papers about like, oh yeah, 99.999% fidelity or 5 nines of fidelity, whatever, right? They're just saying, what is my accuracy of my quantum device and my quantum circuit? So if you do a quantum circuit by itself just on hardware, right, you'll have some fidelity. That's just the probability that you got the correct outcome out. And we can calculate that right here. So this is actually not the exact formula for fidelity. The exact formula for fidelity, close your eyes if you're scared of math and traces and operators, which is valid. This is the exact formula for fidelity. It's very, very not easy. So don't worry about that formula. When you're doing actual quantum error correction and actual quantum computing, you're rarely going to use this exact formula to compute fidelity. The way we usually compute the fidelity is we say, okay, what was the probability I got the answer I expected? Right? In this case, we said I wanted to get a 1 out of the circuit. I took a 0, I flipped it, or I tried to flip it, and I hopefully got a 1. So we can compute the fidelity. and it's 74.85%, the same number that was plotted here. So that's straightforward enough. And then there's also the infidelity, and it's just 1 minus the fidelity. So it's whatever the probability that you got what you didn't want to occur. And so in a simple, really simple circuit like this, I have 1 qubit, no superpositions, no entanglement. I can just say, okay, I wanted a 1, so if I got a 1, that's a success. If I didn't get a 1, it's a failure. So let me just count my successes, and that's my fidelity. And so in this case, it's simple. But if you have superpositions, and you have entanglement, and you have multiple qubits, and all of these things, it gets a lot more complicated to think about. So for today, we're just going to think about single qubit states so that we're only doing fidelities of single qubits. Because when you do have general quantum circuits with multiple qubits and more complex outcomes, you do need to use more complex formulas like the one I showed you. So for today, we're just going to keep it simple. You had a question?
Oh, yeah, I was just gonna ask, this fidelity basically similar to just like accuracy?
Yeah, it's pretty much accuracy. It's technically not like I said, but that's generally how we do it. There is a special type of quantum state called a mixed state when they're not the same. And so a mixed state, we're not going to get into it in too much detail today. I'll like throw the word around. It's basically a state where you don't even know the probabilities of outcomes occurring. You can sort of think about it like, let's say I have 10 decks of cards, okay? But they're all like different. So each of them I've removed like 5 random cards. You don't know which cards. So if I ask you, what's the probability I draw a card and I get a spade? If it was 1 deck and you knew the exact like deck card, like everything in the deck, you could say with certainty what the probability is. But in this case, you don't even know which deck I'm picking. You don't even know what the probability of a card in that deck is. You have a general idea, right? You can assume that from measurements. That's what we do in experiments, but it's not a perfect representation. So if you have a density matrix, it can't be represented like a vector like this because you just don't know the probabilities. So in really complex circumstances like that, which do occur with noise models, you need to use these more complex formulas. And accuracy isn't, it's like characteristically, it's the right word to put on it, but mathematically, it's not correct. So yeah, that's just the preface to everything. For today, we're going to keep things simple, but if you go on to do things in like, especially hardware, you're going to look at density matrices and then traces and things like that a bit more in detail. And that's something that we, talk about when it comes to it. But for today, single qubit, no superpositions, just simple probability of getting the correct answer. So yeah, fidelity, by the way, is represented by this fancy little f. I like it. I think it's a cool f to draw. So if you want to draw a normal f, that's totally fine. People will know what you mean. But yeah.
I mean, mine's not rendering the same as yours. I was just wondering why that is.
Yeah, it's a math command. It might be the case that like certain browsers don't support it, or like if you have like certain version of Colab, that might happen. But yeah, it's an f. It's an f. If you're ever unsure about like what something is in the code, by the way, you can always just like double click and it'll show you all the source code. But yeah, that's all the like really basic like mathematical background. None of that is actually quantum error correction. This is just like words that you want to know about: noise, errors, fidelity, those sorts of things. If you don't fully understand it yet, that's totally fine. This workshop is going to be available later if you want to watch back on it. But does anyone have like general questions about these things? Just from like a vocabulary perspective. Yeah.
Is it a different, it's not for vocab, but is this a different notebook from last week?
Yes, so this notebook is different from last week. Yeah,
Posted in.
could someone post that in the Discord? Yeah, we can post that right now. Yeah, but this is a different notebook from last week. Okay, if there's no other questions on that vocab, let's talk about quantum error correction, why you guys all came here and what we do on our project. So I showed you guys, right? Like noise is there, noise is bad. We can't deal with it in a stupid way by just running a trillion circuits and hoping to get the right statistics. We have to be more careful. And what error correction hopes to do is, instead of just doing statistics about these like outcomes after you measure them, is to proactively prevent errors from occurring, or at least when they occur, be able to detect them. So there's fundamental ideas in quantum error correction, fundamental principles that are both in classical and quantum error correction. One of the most important things that you need to know about for error correction is the idea of the code word. This is what makes error correction work. If you've come to like any previous QCA meeting, you've heard me give this example a trillion times. But let's take the English language, for example, okay? If I want to send you a word or a message, right? There's only so many words that are actual English words. So if I meant to send you hello, and I instead send you like tello with a T instead of an H, you know, okay, tello is not a valid English word. Or in this language, it's not a code word. It's not in our code space, which is our dictionary of all valid code words. So every time you see something that's not in your code word dictionary, your code space, you say, okay, an error has probably occurred. You can't necessarily be certain, and I'll tell you why, but you can assume that an error has occurred. And so once you assume that an error has occurred, it's a question of, okay, what happened? Was that supposed to say like Trello? Because Trello is a website. Or did I mean to say hello? Because hello is also a word. So there's different possible ways that you can decode the errors that occur, right? You look at your word, you take what we call a syndrome. A syndrome is just saying what looks wrong. For example, in this case, the syndrome is that the first letter does not look like it should be part of any English word, any English code word. And that's our syndrome. And we can say, okay, based on that syndrome, we can decode it to an error. So you can say, okay, there's two possible decodings. Either that was supposed to say Trello and I forgot to send a letter, or an error caused that letter to disappear, or it was supposed to say hello and that H turned into a T. Just like here, a 0 can turn into a 1 from the depolarizing error, or it cannot do that. In that same way, letters in classical computing can be distorted and not sent correctly. So these ideas of a code word in the code space are also there in classical error correction, but they're especially important in quantum error correction because noise is so much more prominent in quantum devices today. So you might wonder, okay, we can make this dictionary, right? Like we can say, okay, these are the only valid words. If you send me anything that's not one of these words, I'm going to assume that you made an error or that nature just caused an error and I know I need to correct it. But how do you know that there's an error, right? Like you could say, okay, let me search every possible code word and see, is the code word you sent me in that list? And in English, that works, right? There's only finitely many words. You can go to a literal dictionary, look up the word. If it's not there, you know it's not a code word. But what's different about quantum computing? In quantum computing, you have infinitely many states. 0 is a valid state, 1 is a valid state, but so is any superposition. Any vector on the sphere is a valid state. So how do you know if something's in your dictionary, right? If there's infinitely many states. One way that we do this is by restricting the sphere. So there's like a little like analogy, which actually mathematically is very like profound of a analogy to make. But think about like a grid, right? Like when you're plotting things on a grid, you might have coordinates, right? So you'll have like 1, 2, 3, and you'll have 1, 2, 3, right? And you can plot points on your grid. And you can say, okay, every word is a point on this grid. You might already notice that means every word is a vector and quantum states are vectors. So this is already really profound of an observation to make. Every point is like a point on the grid. It's a vector on this plot. But what I'll say is for quantum error correction, I'm going to only restrict my code space into points that are along the x equals y line, this diagonal. That was a terrible line, but that's my code space. If I give you a point like 1, 3, okay, 1, 3, this is not a valid code word. It is not in my code space, this line. If I give you instead a point like 2.5, 2.5, that is on my line, so that is a code word. And now I say, okay, that seems like a valid state. I'll accept it and move on. That's what it means to be a code word. And so there's this question of saying, how do you know whether something's a code word, right? Like again, on this line, there are infinitely many states. You could say, oh yeah, like any point on this line is a code word, right? Like we restrict it a little bit, but it's still infinite. And you need a more finite, a more discrete way to say, okay, if I look at a state, I know with some really high probability it's an error or it's not an error. And the way we do this is something called a stabilizer. A stabilizer, you can think of it as a quantum operation that looks at any quantum state and says, is this a code word or not? If I apply my stabilizer operation to a valid code word, something that's in my code space, I'll get a +1. If I apply my stabilizer operator to something that's not in my code space, so it's not a valid word, it's like hello, it's not in my dictionary, it's not along my line, it's somewhere else, it's not a valid code word, I'll get -1. And that's the beauty of how quantum error correction was developed. Researchers realized that if you take these special operators and you multiply them by special vectors, then you'll get these special plus and minus relations. If you've taken linear algebra 1 or 2, you'll know that this is something called an eigenvector. So this is like the math statement that I've written here. So it's S times your vector, where S is your stabilizer, gives you plus or minus 1. It's the plus and -1 eigenvalues. And so we basically say in quantum error correction, our code space is going to be the eigenvectors of our stabilizers, the +1 eigenvectors. So any quantum state, which when multiplied by your S operator gives you a +1, is a valid code word. So now I can do quantum error correction. You send me a quantum state, or you prepare a quantum state, and you ask me, or you just give it to me, right? And I ask myself, is this a valid code word, or was there an error that occurred? Okay, and what I do is I say, okay, you gave me this quantum state, you prepared it in a quantum circuit, let me apply my stabilizers. Let me multiply them by these operators. If I get a +1 when I multiply it, it's valid and I accept it. That's what you meant to send me. If I get a -1, there's an error. And based on where I get a -1, I say, okay, that means that there was an error around here. And now let me try to decode it. Does that general concept make sense? I'm going to show you more explicitly how this works in a quantum circuit, but again, yeah, software questions. Yeah.
You might be getting to this, but how are you performing an operator on a state without affecting the state?
Sorry, can you repeat that?
How are you performing an operator on the state without affecting the state?
Right,
Is it
yeah,
because
and
it's
we
along the eigenvector?
yes, it's an eigenvector, that's why. So we don't care about that +-1 part. It's still the same state.
Okay.
There's just, if you know the term global phase, all you've added is a global phase. And so you can measure that global phase in special ways, but it doesn't affect your underlying quantum state. So that's how you can do this without destroying your quantum information. There's a very clever way of doing it called oscillocubits, which we will see in due course. But yeah, if there's no general questions about the concepts and the words I mentioned, I'm going to show you guys what this actually looks like. And hopefully once you see like what it looks like, it'll make a bit more sense. So let's get into quantum error correction with Qiskit. So we start again, we make quantum registers. For now, don't worry about what all these quantum registers mean, why they're there, what their names mean. I'm going to explain them as they come along. Okay, but the point is we have all these quantum registers that we need. And so we start off by making a quantum circuit. Like always, right? We make a quantum circuit that has all of our quantum classical registers. So when you draw this, you'll get a blank quantum circuit. So it's a fresh slate to start out with. And so we say, okay, this time I want to do an X gate, right? I always wanted to do an X gate. I just don't want there to be error. So again, let me apply an X gate to what's called my data qubit. These are the qubits that store your actual quantum information. So there's a lot of other qubits here, which we're going to use for probing this quantum state and doing other computations. But our underlying data is stored in these data qubits. And so any quantum operation we do affects these data qubits. It transforms them into other states. And so once we apply this operation, we can say, okay, I made my quantum circuit. Now let me apply error correction. If I run the circuit right now and do measurements like I just did before, this is the same quantum circuit, I'm still going to get those really bad numbers, like 75% and 25%. So I don't want to just run it now. I want to apply quantum error correction so that if noise occurs or an error occurs, I can correct it. So what does that look like? First, we have to take this quantum state, really simple, just 0 or 1, and encode it. This is a very important step. So what's basically happening is I'm saying, okay, let's say I have a quantum state 0. I don't want to just store a 0 because if one bit flip error occurs, it's going to turn into a 1. And now I'm confused. That's a 0% fidelity. I went from exactly the state I wanted, 0, to the opposite state, 1. So I can't just store 1 qubit. What I can instead do is I can spread my information across multiple qubits. So that's why the quantum error correction code we're going to be looking at today is called the bit flip repetition code. You're repeating the information across multiple qubits. So, oops, did I delete a line? Def QC encode. If I run this, I get these operations.
So are you copying the one qubit to another? 'Cause I thought that was not.
Yes, so you can't copy the state exactly. If you're doing classical computing, you can copy it exactly. And okay, sorry, I also lied earlier. This is not for the quantum X gate itself. This is just for like encoding. So this is preparing my quantum state. So I prepare it in the one state, okay, and then I do a C naught gate. So if you remember, a C naught gate says, look at my control qubit, so this first qubit here, and see, is it in a 0 state or a 1 state? If it's in a 0 state, do nothing. If it's in a 1 state, then apply a NOT gate to my other qubits. So if you want to visualize this, the way it works, or like write it out in terms of quantum states, is you start out with a single qubit in the 0 state, and you say, okay, if it's in the 0 state, I'm going to put my other two qubits also in the 0 state. So I go from this to 0, 0, 0. Okay? And if it's the 1 state, then I go from this to 1, 1, 1. If you don't trust me, you can flip like one of the qubits and you'll see, yes, this is actually what's occurring. But all I'm doing is I'm propagating this information by using these C naught gates to share it with other qubits. I'm not copying the qubit. This is not copying the qubit. I happen to be doing a quantum operation that is dependent on the state of one to the state of another, but it's not copying. That's very important, okay? So once I do this, what basically happens is I have 3 qubits that store the same piece of information. So now, let's say that depolarizing error occurs, right? Like I wanted to flip from 0, 0, 0 to 1, 1, 1, but instead I do like maybe 0, 0, 0 to 1, 1, let me write it here, 1, 1, 0. Now you can look at this and you can say, okay, you sent me 2 ones and a 0. This is not in my code space. My code space was 0, 0, 0, 1, 1, 1, and any superposition of these. Okay, any superposition of these logical states. But this is not a superposition. It's not a linear combination of these two kets. And you can verify that if you want yourself by saying, okay, if I add this and that, I'm just never going to get this, okay? I can get 0, 0, 0, I can get 1, 1, 1, I can get, if you remember, I can get arbitrary alpha 0, 0, 0 plus beta 1, 1, 1, but I can't get that. That cannot be written in this way. So now I look at this and I say, okay, an error has occurred. I do syndrome measurements with stabilizers that I'll show later, but I can say, okay, so an error occurred. My syndrome says this qubit had an error. It's not supposed to be a 0. I'm inferring it's not supposed to be a 0, so I can apply a correction and make it a 1. Okay? That's error correction in action. And that's why we want to do these control NOT operations. So that we can say anytime we do a quantum operation, we know it has to be a superposition of these states. It's not going to be something random like 1, 1, 0 or 0, 1, 1. The place this breaks down is if you have 2 errors, right? So here I said one of my bits, I meant to go from 0, 0, 0 to 1, 1, 1, but I went from 1, 0, 0, 0 to 1, 1, 0. And I was able to infer it's supposed to be a 0 or a 1. But what if I have 2 errors occur? Okay, now I have 2 zeros. Now, if I were to look at the state, if you just showed me the state with no prior information, I would say, okay, that's supposed to be a 0. It's not in my logical code space, but it has mostly zeros. So let me just guess it's going to be a 0. But really, you meant to send me a 1. It's just that 2 of the qubits had an error. So this is the limitation of really simple quantum error correction codes like the one we're looking at today. When you only have 3 qubits, just having 2 or 3 errors is enough to completely throw me off. And so you need more complex quantum error correction codes. For today, we're not going to construct those because it's hard to visualize those as quantum circuits and there's a lot more qubits. But just know this is a limitation of the code. But for now, it works, okay? We're going to assume that we have low enough errors that that won't occur. So we're able to just almost copy, not exactly, but almost copy this quantum state into the other qubits. Okay, so now we have 0, 0, 0 or 1, 1, 1. Now you can, at this point, you can do one of 2 things. You can move on and say, okay, I want to do more quantum computations. Maybe I did that X gate, but I actually want to do other quantum gates. Maybe I want to do like Shor's algorithm and I have more qubits, right? At this point, you can do that. You've encoded your quantum state. Now, if an error occurs, it'll have to be outside your code space. It'll have to turn it into a non-code word for me to not detect it. Or you can just do the full quantum error correction process, which is what we'll do for today for simplicity. Yeah.
So if you, like, C naught has some level of infidelity, right?
Yeah, so that's absolutely true. Yes.
So like, as you scale up the number of qubits you use, you're eventually gonna run into something where C naught being infed.
Yeah, it'll having too much infidelity or having low fidelity.
So
Yeah.
does that imply there's like a optimal number of qubits?
Yes, there is not an optimal number necessarily. We don't know that. That would be a Nobel Prize if you could find that. But we know that there's a threshold. And that's something that I'll show you later with this exact code. I'm gonna show you that this code has a very low threshold and it's really easy to make it just not work. But yeah, we'll see that at the end. So that's called a threshold, and it's something that we do research as well for QCA. But yeah, I can do more quantum operations, do more X gates, Y gates, whatever quantum algorithm I want to do, or I can go and get to the very end where I do quantum error correction, where I say, okay, I've encoded my quantum state, I've been doing operations. Now let me see if I can check for errors, figure out what those errors are, and correct them. You have a question?
Yeah, can you do the same error correcting codes as you can with classical signals?
Not necessarily. This is, for example, because of the no cloning theorem. So, a lot of classical codes will use repetition or cloning, where they'll copy a bit 50 times and say, okay, let's do majority voting. But you can't copy quantum information. So that already rules out a lot of classical codes. There are special quantum error correction codes that are formed from classical error correction codes. So one of the codes that we look at for QCA, one of our first codes that we did, the Steen code, is a quantum Hamming code. It's formed from classical Hamming codes, if you're familiar with those. Don't worry if you're not, but you can form quantum gate error correction codes from classical ones. It's just not trivial. You can't copy it over. Yeah. Any other questions before we go into the full QEC cycle? Yeah.
Yeah. I'm a little rusty on my classical error corrected codes, but if I remember correctly, the asymptotics of them are fairly advantageous. Like if you have a large number of data, you need only a small number of additional bits to have an error correcting code on it. Is that still the case with quantum error correcting codes?
You say what you mean by if you have a large number of bits, you don't need that much.
Like they get more efficient as they scale up.
That is, okay, I would be careful about what you're saying by efficient, right? Because if you have a quantum error correction code, right, which has 1 million qubits in its logical encoding, then yes, you could say oh yeah, the probability that an error occurs that I don't detect is really low. But at the same time, you have 1 million qubits that you need for one logical qubit. It's is that advantageous? Is that efficient? In reality, it's not. Practically, it's not efficient, right? You want to minimize the number of logical qubits or the number of physical qubits you need in your quantum circuit. So here, we will need 5 to do this 3 qubit repetition bit flip code. If you can minimize that number, that's great. But as I just said, if you minimize the number, you're not going to have as much what's called distance, which is how far you can go before you're not able to correct errors effectively. So there's trade-offs to it. Yeah.
I just meant I think I could be wrong about this. I think Hamming codes have a logarithmic.
Yeah, there's scalings like that. Yeah, those sort of things apply for quantum error correction codes as well.
Okay.
I don't remember the exact scalings, but yeah, they have scaling. So if there's no other questions, then we can talk about the quantum error correction cycle. So we did encoding, we took this really simple 0 or 1, and we made it into a seemingly more robust state. But what can we actually do with this more complex state? We do a syndrome measurement. So I mentioned this a bit before, but let me just draw it so that you can look at it. What we're basically doing at this point is we're saying, okay, let's take our quantum bits, right, our data qubits, which are storing our quantum information, like the 0001111, or some superposition of these 000s and 111s, and let's do some more quantum operations, which correspond to our stabilizers. So I told you these stabilizers are like quantum operations that you can apply, and they'll tell you whether you're in a 0 or a 1. The way that you apply them without doing a quantum actual measurement that demolishes your state is you do them under a controlled operation. So for example, I have a stabilizer, which is xxi, okay? So I turn that into C naught controlled I. Okay, let me write that out to be more explicit. I start, my quantum stabilizer might be x, x, I, okay? And I turn this into Cx, Cx, Ci, which is just equal to I, okay? By doing this as a controlled operation, you actually don't need to do a measurement, and so you don't demolish the quantum state, because this is just a quantum operation. There is nothing demolishing about this. This is just another regular quantum information. But what's nice about it is it looks at your quantum data qubits, okay, the ones that are storing your information, and it sort of does almost a measurement of their state into these guys. These are your ancilla qubits. These are the overhead that come with quantum error correction. You say, okay, I have the data in my data qubits. Now let me do these stabilizer measurements, as they're called. Okay, different from regular measurements, stabilizer measurements, where I just take my stabilizers, the things that check whether or not something's in the code, and do them as controlled operations, just like this. Okay, so by doing these controlled operations, I can get a syndrome in these ancilla qubits. So now these two guys, these two qubits, store the syndrome. They tell me, is my quantum state a code word with respect to this stabilizer? And so in this case, I have two what are called generating stabilizers. These two generate my quantum error correction code. So by measuring, doing a stabilizer measurement of these two stabilizers, I get the syndrome measurements. Don't worry fully just yet how you go from like XXI to these quantum operations. There's a little bit of math involved. This is the whole like row reduction and base 2 thing that I told you guys about in last week or the week before. But we know how to go from these stabilizers into special quantum operations that will put syndromes in the ancilla qubits. So just to recap quickly, we have data, there might be an error, we do these stabilizer measurement operators, and it puts the syndromes into our ancilla qubits. And now these ancilla qubits can be measured, okay, without demolishing your quantum logical qubit. The reason why is that you have your ancillary information, your syndromes, in different qubits than your original data qubits. Your information is still stored in the data qubits. Any superposition, any entanglement is still there in those data qubits. But you measure these other guys, which happen to be correlated because of your stabilizers with your data qubits. So now I told you about like, oh yeah, if you take like a non-code word and apply a stabilizer to it, you'll get -1. That -1 will show up in the measurement. If I measure a 0 for this ancilla qubit, what that means is this stabilizer said no syndrome, as far as I could detect. If I measure a 1 on this qubit, that means this stabilizer said, I detect what seems to be an error. Okay? These operators are still noisy. They're still quantum operations. They could be wrong, but we have to trust something, right? We have to make base assumptions. And we're assuming that these measurements are high enough fidelity that we can trust what they say. So we say, okay, let's do these syndrome measurements. Let's get these syndromes, and then let's measure them, okay? Once we've measured these syndromes, then we know, okay, if I have a 0, 0, that means I have no errors. Or if I have a 1, 0, that means I had an error on my first qubit, but not my second qubit, that sort of thing. And so that's where that last step comes in, where you say, okay, let me look at my syndrome measurements and apply a feedback gate to the measurement circuits. So that part, again, it's like there's math behind it, and don't worry too much about how these gates are come up with. But the idea when you want to take home is I can do these measurements and I can use them to infer whether or not I'm in an error state or a non-error state, a code word. So to figure that out exactly, you have to do decoding. So here, this is where you actually look at your classical bits and you say, okay, if this guy was a 0 and this other guy was a 0, then I need to apply this correction. Okay, so each of these ifs, they're conditional operations. They say if this classical register was in a special state, so for example, here it's 3. That means I had 3 ones. Okay, then that means, okay, that means I need to apply some correction, and that happens to be this correction. If I get a 1, I need to apply this correction. If I get a 2, I need to apply this correction. This is the decoding step. We said, okay, based on these syndromes that we measured using our stabilizers, multiple stabilizers, we can put them together and we can say, okay, if these specific combinations occur, these are the errors that actually occurred, and we can apply the appropriate corrections. And at the very end of the day, you measure everything, you still have to do final quantum measurement. Hopefully by now, these 3 gates corrected any errors, okay? All of error correction happened between this gate and this last gate. I encoded into a protected, robust state. I measured my syndromes into classical bits. I read them out and have tried to make corrections. And hopefully after I make corrections, I can measure my quantum state. And now I can say, okay, with some better certainty than before, this is the correct answer. And so let's try it again. Let's see, is this actually the correct answer? So we can do the same. This is basically the same code as before. I was a little bit sneaky and I cheated by making the parameters smaller, but this will get into the threshold number. So actually, you know what? Let's not cheat. Let's make this 0.5. Initially, we ran it with our error parameter being 0.5. This is roughly a 0.25, or not 0.25, 25% chance of having not what you wanted occur. So that's really bad. And as you'll see, once I plot the data, QEC didn't help. Actually, I think this data is actually worse now. Actually, maybe it's a little bit better, but it barely helped, right? It's still 75-25. The reason is this code doesn't have enough threshold. It doesn't have enough error it can tolerate before it cannot correct errors. Just like I showed you here, if 2 of these bit flip errors occur, I'm going to make the wrong decision, even with quantum error correction. You have to be below a certain threshold that depends on your quantum error correction code and your error protocol in order for it to work. So if I make my parameter like 0.01, then hopefully this code's not that bad. There we go. We got 99% accuracy, 99.38 fidelity. So that's a lot better, right? There's still some error, and again, it has a threshold. At some point, it's just not going to be perfect. Okay, there's going to be some amount of error, some special error that occurs, and it just completely wipes out your fidelity. That's why we construct more robust quantum error correction codes. That's what our project is all about. We can do this, right? We can have 3 qubits, 2 ancilla qubits, and just do and assume that if all our errors are really, really small, everything will be perfect. But that's not how it works in reality. In reality, you have a lot of noise, a lot of different types of noise. You don't even know how to model all the noise in your system. So you have to form more robust codes. You can't just say, oh yeah, let me copy my state 3 times. That's not going to work. You have to do something more complex. And our project basically says, can we construct more complex error correction protocols? So can we use more than 3 qubits? Can we use special codes? Can we do special types of stabilizer measurements? Like here, I literally just measured the stabilizers directly onto my ancilla qubits. But can I do something more complex? Can I measure them in special orders? What if I measure them all at the same time instead of back to back? By doing all these special tricks, we hope that we can increase this threshold and increase our fidelity, even for the same error rates and the same codes. So that's really what error correction is. We took a really noisy state, one that's not robust, we made it more robust, and we tried to say, can we detect and correct errors? And hopefully at the end of the day, if we're within threshold, we can, and we get 99% fidelity. And at the end of the day, you need much better than this. So there's a lot of work to be done. Classical computers, their errors are like 10 to the minus 13 and less. So you cannot tolerate like 99.38% accuracy. You can't tolerate 0.62% accuracy. It's just not going to take you anywhere. So that's what our project's all about. And if you're interested, then you should join our project. It's 7, so if people need to go, feel free to. But if not, I'm going to try and demonstrate to you how our own quantum error correction library works. So there's all this code that we wrote, right? I'm just using scroll. There's all this code we wrote, and there's all of the math that I said, don't worry about the math, we know how to do it. And I just shoved it all under the rug. And so, you might wonder like, okay, what if I don't know how to do the math? What if I don't know what my stabilizers are? What if I don't know how to construct them? What if I don't know the decoding maps or the correction schemes? If I don't know any of that, that's where you use LogicalQ. LogicalQ says, okay, don't worry about any of it. If you can write a quantum circuit in Qiskit, you can write it in LogicalQ with error correction. So just to demonstrate quickly, and by the way, this sometimes like, for some reason, it requires you in Colab to restart the notebook. So if you have that error occur, then just restart, click restart session and run all, and that should make it work. But what we basically do, we install this guy, probably not gonna work the first time. It works perfectly fine locally. It's just because we're trying to do this on Colab so we can share the notebook with you guys. Colab's not the best for programming. I don't recommend using it for like long-term stuff, but just for now, it's also really slow. But while it's doing that, okay, cool, yeah. So I can show you, for example, logical circuit. So just like we made a Qiskit quantum circuit, we can make a LogicalQ logical circuit. And so if we scroll up, we see the exact same things I told you about. So there's logical data qubits, storing my quantum information. I have ancilla qubits, and even more ancilla qubits, lots of ancilla qubits. And I have gates like this, the encoding operation. All I had to say was make a logical circuit using the Stein code, the one I told you about, which happens to be a quantum Hamming code, and I can encode it. So I can encode the 0 and 1 logical qubits into the states 1 and 0, and it'll do all of the encoding for you. And then you can draw it out right here, and you can see, oh yeah, it applied an encoding gate to one qubit and to another, right? And then you say, okay, cool, so I encoded a logical qubit. Now what do I do with it? Anything you want. So I can do logical circuit dot Hadamard. So I can apply a Hadamard gate. And then when you visualize that, you'll see right up here, you have a Hadamard gate, right? That's a logical Hadamard gate. This subscript L tells you it's not just a physical Hadamard gate like we've been drawing for like this workshop and the previous one. This is a logical gate which can be quantum error corrected. And so you apply this Hadamard gate, and so let me just clear the output, and you can do QEC. So I told you like, oh yeah, to do stabilizer measurements, there's all this like Gaussian elimination base 2. No one wants to do that by hand. So you can just say append QEC cycle, and it'll append at the very end a QEC cycle. So now all of the quantum error correction is wrapped inside this little box, okay, for each logical qubit. And so it'll do all of the detection, the measurements, decoding, and correction for you. And at the very end of the day, you can do measurements just like this. And so it appends measurements at the very end, just like we did before. You know, we measure all of our data qubits. And then you can run this and you'll get better fidelities. So that's really what we're aiming to do with this project. We're aiming to be able to generalize quantum error correction with more robust schemes, with more usability, with more tricks and these different things that can help us increase our fidelity without having to compromise efficiency and computational cost. And on the hardware side of things, we're hoping to optimize when are we doing these quantum error correction cycles, right? Because quantum error correction by itself is noisy. It's not perfect. You have to do quantum operations to correct your quantum operations. It seems circular, but it's the way it has to be. And so there's this question of if you do QEC too much, it's not going to be beneficial. You can only do it a certain amount. And so what's that perfect amount? What's the optimal amount of QEC that you do? And that's what our hardware paper that we're working on right now is doing. So if you're interested in that, definitely let us know. Now that you guys have been to last week's workshop and this week's workshop, you're pretty much ready to start, reading like more advanced materials in quantum error correction and papers and start contributing to the project. So if you want to do that, send a message on Discord, say like, hey, I think I'm more interested in this part of the project or what's available, and we'll answer your questions and get you started on when you can look at. In the meantime, we have these extra resources if you guys want to look at them that are really useful for, going over everything I told you about today, but with more math, more details so that you understand it a bit more. But as always, if you have questions, throw them in the Discord, even if it seems stupid, totally just send it and we will help you out with whatever you need. And yeah, that's the QEC workshop. Thank you guys for coming, and we'll be around a bit longer in case anyone has questions.
Cool.